Hello, welcome to Mystery Science. This very short video is going to be part of the CP2 part of the Edexcel GCSE Combined Science course. CP2 is about forces, CP2b is Newton's first law. Isaac Newton was an incredibly brilliant scientist and has come up with 3 fundamental laws of the universe without which the entire universe will fall to pieces, and we'll discuss this in more detail. So we're going to look at describing the effects of balance forces on moving and stationary objects. We're going to describe what non-zero resultant force actually means and what that means for an object that resultant force is being acted upon. Right, so the do now for this is going to be another recap of scalar and vector quantities, just to describe the difference between those, and to draw a diagram of a car showing balanced forces. Check out my previous video, CP2a, for information on how to do that. While you're doing that, once again, I'm going to plug this t-shirt, this LGBTQ+ neurodiverse ally shirt. This is available on Amazon through the link below. And also, if you want stickers, mugs, travel mugs, that kind of thing, check out my Redbubble store. All right, so the difference between scalar and vector quantities. I keep saying vector quantities is, so a scalar quantity has a size. For example, a speed. If you're going 20 miles an hour, you're going 20 miles an hour. If you're going 20 miles an hour this way, this way, this way, this way, your speed is the same. But a vector quantity has a direction. This vector and this vector are completely different. Even if they're both going at 20 miles an hour, the direction is important. Okay, so if you've drawn a diagram showing balanced forces, what you should have drawn is any object with arrows in opposite directions, but they both have the same size. So the arrow going in one way, let's say for example is 10 newtons, the arrow going the opposite way is also 10 newtons, but crucially in your diagram they should be exactly the same size. Alright, so let's have a look at Sir Isaac Newton's very first law of motion. Now, a lot of teachers who aren't physics teachers come to me and say, Mr. E, how on earth do I teach Newton's first law and make it vaguely interesting? And I say, what do you mean? What's wrong with you? Newton's first law, the fundamental law of the universe. Look, this object right here, right there, that object there is exhibiting the fundamental law of the universe. How is this not exciting? Without these laws of the universe, everything breaks down, and physics as we know it is completely insane and will break apart and the universe will collapse. We don't want that. But look, this object right here is doing the very thing that Newton described to make everything make sense. What's it doing, Mr. E? It's doing nothing. It's not moving. That's crucially important. All of the forces on it at the moment, there are forces acting upon it. I'm holding it in front of my camera, which means that there is weight pulling it down. The weight of the pen, if I let go of this, it will drop. So that means there's a force acting on it. But I'm holding it up, which means there's a force holding it up. And because it's not moving, these forces are balanced. So the force going in this direction is exactly the same as the force going in this direction. And actually, if there were any sideways forces, they're exactly balanced as well. And so this is Newton's first law. An object at rest stays at rest unless an external force is applied. So this is a very important law of the universe. This means that anything, if you look around you, everything that is stationary is currently obeying this very fundamental law of the universe. Without that law of the universe, these things would be all over the place, hitting you in the face while you're trying to do your work. And that would suck. So what does this actually mean? It means that without applying an external force, a resultant force to this thing isn't going to move anywhere. Now, Newton's first law comes in 2 parts, and the first part is easy to remember. An object at rest stays at rest. If it's not going anywhere, it's never going to go anywhere unless you give it an extra force. But the second part is a little bit more confusing, but it's essentially the same thing. If this object was moving, if we were in a classroom and I hurled it at 5 meters per second, if we ignored air resistance and it carried on traveling at 5 meters per second, then again, there would be no external forces on it. All the forces would be balanced. And if the forces are balanced, the object moves at the constant speed. So really, it's just one law. An object will maintain its motion and its speed unless an external resultant force is acting upon it. So if its speed is 0 at rest, it will stay at rest. But if it's moving at 5 meters per second, if the objects of the forces are balanced, then it will stay at 5 meters per second. Let's have a look at some examples to try and help this make a bit more sense. Before we look at some examples, actually, we should probably get down a definition in your book or on your paper, just so that you're active and engaged. So this is a simple closed passage exercise. Pause the video, fill in the blanks. So write the passage and fill in the blanks with the key words. Okay, welcome back. So Newton's first law, an object at rest stays at rest unless acted upon by an external force. But let's look at it this way. A moving object will continue to move at the same speed and direction, that's important, unless an external force acts on it. Likewise, a stationary object will remain at rest, so not moving, unless an external force acts upon it. An external force is any force that you add to it. Okay, so without an external force, the motion of a body does not change. That is Newton's first law. So if it's at rest, it stays at rest. If it's at constant speed, it stays at that speed. The motion does not change. Forces change the motion of an object. That's what they do. So if you have a resultant force, that determines the velocity of your object. Okay? If the forces are balanced, the velocity does not change. But if your forces are unbalanced, the velocity changes. It accelerates. It gets faster and faster and faster, or slower and slower and slower. So an unbalanced force accelerates or decelerates an object, or changes direction. Remember that velocity can be a constant speed but in a different direction. So if an object is moving in a circle, which we'll look at in a later lesson, then the speed is staying the same, but the direction is constantly changing. So the velocity is constantly changing because its direction is constantly changing. This means there is a resultant force changing the direction. So it's accelerating, even though its speed stays the same. But we'll look at that in another video. Alright, so let's look at an example. Here we have a boat with wind in its sails. It has a forward force from the wind in its sails of 300 newtons, and it's travelling at a constant speed, so that's crucial. Using Newton's first law then, we know what the force acting backwards on the boat is, because it has a force going forwards and it's moving at constant speed. Explaining your answer, write down in your book or on your piece of paper, whatever it is, what is the total force acting backwards on my sailing boat? All right, so hopefully you're able to understand that if the constant of the speed of the boat is constant, then the forces must be balanced. The force going forwards must equal the forces going backwards. Therefore, the total force acting backwards on the sailing boat from the water resistance is 300 newtons. So let's consider another example. Let's say that the lake that our original sailing boat on was frozen over. And so this person has got an ice yacht. This is an amazing looking thing. So it's essentially a yacht with blades instead of sitting in the water. So now we still have 300 newtons in the sails, but my ice yacht is getting faster, it's accelerating, it's increasing in velocity. It's the same conditions. I've got the same force in the forwards direction, but instead of water, I've got ice. Why is it increasing velocity? Explain your answer again on your piece of paper or in your book. Okay, so hopefully you've worked out that ice obviously has less friction than the water. The water is going to have quite a lot of drag, whereas this thing is built for incredibly streamlined. So the force in the backwards direction is not as large as the force in the backwards direction in our water example. So this thing has less friction. It's on ice. This looks like amazing fun. I want to have a go at this. So because there is a resultant force, the force in the forwards direction is bigger than the force in the backwards direction, we can calculate the resultant force, taking away the friction from our 300 newtons, whatever that may be, and we would find that you'd have a resultant force bigger than 0, therefore it's accelerating and getting faster and faster. All right, let's imagine for a moment we've gone to the circus and a human cannonball is about to be shot out of a giant cannon and into a safety net. The human cannonball stands on a platform inside the cannon. It's not an actual cannon. And what happens is he's standing on a platform. That platform then is pushed at very high velocity up the cannon with him standing on it. And then he obviously then flies through the air, slows down as he arcs through the air, and then falls back towards the ground and lands in a safety net. So what I'd like you to do is just draw very quick diagrams of each of these stages, and then just write 1 or 2 sentences that describe the forces from the box there that's acting on the human cannonball, and whether there's a resultant force at that time, which way it acts, and how any resultant force will affect their movement. Again, pause the video, do that section, and then come back. All right. So our human cannonball 1, he's waiting to be fired. He's standing on a platform. So his weight is obviously acting downwards towards the center of the earth, but the force from the platform is pushing back up on him, okay? And he is not experiencing a resultant force. The forces on him are balanced, therefore there will be no change in his motion. When he's being fired, he's standing on the platform and it's being pushed upwards. So let's focus on the forces on the human cannonball. He still has weight acting downwards towards the center of the earth, but the force from the platform is now very much higher, and so is acting in the upwards direction. So now there's a resultant force because his motion is changing. He is getting faster. And as soon as he leaves the cannon and he begins flying through the air, his weight obviously is pulling him back down towards the center of the earth. Air resistance is also acting on him in the opposite direction. There is no force from the platform. There is no other forces acting upon him. There is a resultant force acting downwards, but because he's shot out of the cannon with a velocity, he is slowing down. His motion is changing. He's slowing down and slowing down and slowing down until eventually he stops accelerating upwards. No, sorry. Eventually he stops moving upwards. He's always accelerating downwards. And then his velocity is going to increase going downwards. It's going to get faster and faster. And then he's going to land in the safety net. Now the force from the net is going to be acting upwards. The force of his weight is acting downwards. And again, he's in a situation where his forces are balanced and he's come to rest. Okay, we're going to go through a very quick quiz now. I'm going to show you a bunch of images. There's just 5 of them. And I want you to write down what the resultant force is and which direction the resultant force. Okay, so question 1, is the football accelerating, decelerating, or maintaining a steady speed? If you said it was accelerating in the direction of travel, congratulations, because it has a force of 8 newtons on one side and 6 newtons on the other, so it must be accelerating. Question 2. This bird is falling at a steady speed. Give the size of the unknown force. This one here. Okay, if you said this force was 20 newtons, congratulations, because it's falling at a steady speed. Its weight is 20 newtons. Because it's a steady speed, it must be a balanced force of 20 newtons. Question 3. What happens when the force in red is applied to the balloon? Well, if you have a force going this way, this is a constant speed at the moment because its force is balanced. But when you add this, it's actually going to start moving in this direction. It's going to accelerate. Okay, we have the Hunger Games trilogy. What is going to happen here? Calculate the resultant force acting upon these books. Well, in the vertical direction, we have 2 newtons of weight and we have 2 newtons of upthrust. So this is balanced. They're not going to go anywhere in this direction. However, there is a force of 5 newtons pushing them this way. There is a force of 12 newtons pushing them this way. The resultant force, therefore, is going to be 7 newtons in this direction. Okay, let's have a look at this car then. Are the forces acting upon this car balanced? And the answer is no, they're not. In the vertical direction, they are. You've got 23 newtons pulling down, 23 newtons pushing up. But this car will be accelerating in this direction because it's got a drag of 17 newtons, but a forward force of 30 newtons, giving you a resultant force. Okay, to round this off then, I would like you to just do a little pyramid plenary, please. Put on the top any question you have about the lesson. In the middle, things you've been reminded of today. And at the bottom, things you have learned today. All right, stay safe. I'll see you soon.